The human brain is an extraordinary organ. It is a complex network of billions of neurons. These neurons communicate with each other through electrical and chemical signals. This intricate network allows us to think, learn, and experience the world around us. Artificial intelligence, or AI, aims to replicate this remarkable capability. It seeks to create machines that can perform tasks that typically require human intelligence. One of the most powerful tools in the AI arsenal is the neural network. Neural networks are computational models inspired by the structure of the human brain. Just like our brain uses interconnected neurons, neural networks use interconnected nodes or artificial neurons to process information. These networks are designed to learn from data, recognize patterns, and make decisions. In essence, neural networks bridge the gap between human intelligence and machine learning. They are the driving force behind many AI breakthroughs that are shaping our world today. Imagine a network of interconnected points, much like a spider web, intricate and complex. Each point in this web represents an artificial neuron, a simplified version of its biological counterpart, designed to mimic its function. These neurons are organized in layers, forming a pathway for information to flow seamlessly from one point to another. The input layer receives information from the outside world, like an image or a sound, converting it into a format the network can process. This information is then passed through hidden layers, where complex calculations and transformations take place. Each connection between neurons has a weight associated with it, determining the strength of the signal being transmitted. As the information traverses the network, these weights are adjusted based on the learning process, refining the network's accuracy. The network's goal is to adjust these weights so that the output layer produces the desired result, such as correctly identifying an object in an image or recognizing a pattern. This learning process, known as training, is what makes neural networks so powerful and versatile. By adjusting the weights of connections, the network learns to recognize patterns, make predictions, and perform tasks that would be difficult or impossible to program explicitly, showcasing the potential of artificial intelligence. The concept of neural networks dates back to the mid-20th century. In 1943, Warren McCulloch, a neurophysiologist, and Walter Pitts, a logician, created a computational model of a neuron called the McCulloch-Pitts neuron. This groundbreaking work laid the foundation for artificial neural networks. In 1957, Frank Rosenblatt, an American psychologist, developed the perceptron, the first artificial neural network capable of learning. However, early neural networks faced limitations. They struggled to solve complex problems, and enthusiasm waned. The field experienced a resurgence in the 1980s with the development of backpropagation, a powerful algorithm for training neural networks. Today, neural networks are more sophisticated than ever. Advances in computing power, data availability, and algorithmic innovation have propelled the field forward, leading to breakthroughs in AI. Section 4. Learning and adapting training neural networks. Training a neural network is like teaching a child to ride a bike. It requires patience, guidance, and consistent effort. At first, there will be wobbles and falls, moments of uncertainty and imbalance, but with practice and feedback, the child learns to balance and ride smoothly, gaining confidence with each attempt. Similarly, a neural network learns from data, adapting and improving over time. We feed it a massive data set, rich with information, like images labeled with the objects they contain, providing clear examples for the network to learn from. The network makes predictions based on its current weights, which are its internal parameters, and we compare these predictions to the correct labels, assessing its performance. This comparison generates an error signal indicating how far off the predictions were, which is then propagated back through the network, informing adjustments. The network adjusts its weights based on this error signal, refining its internal parameters, effectively learning from its mistakes. This process, called backpropagation, is crucial for learning. This process is repeated countless times until the network achieves a desired level of accuracy, improving incrementally. Through this iterative process of trial and error, the network continuously refines its understanding. The neural network learns to recognize patterns, minimize errors, and enhance its predictive capabilities and improve its performance on the given task, ultimately becoming more accurate and reliable. Section 5. A network of networks. Types of neural networks. Just as there are different types of neurons in the human brain, there are different types of neural networks, each designed for specific tasks. These networks mimic the way our brain processes information, allowing machines to perform complex tasks. Convolutional neural networks, or CNNs, excel at image recognition. They are particularly good at identifying patterns and features in visual data. They use filters to extract features from images like edges, corners, and textures, making them ideal for applications like facial recognition and medical imaging. This ability to detect intricate details makes CNNs invaluable in fields requiring high precision. Recurrent neural networks, or RNNs, are designed to process sequential data such as text or speech. They are adept at understanding context over time. They have a memory of previous inputs, making them suitable for tasks like language translation and speech synthesis. This memory capability allows RNNs to generate coherent and contextually relevant outputs. Generative adversarial networks, or GANs, consist of two networks that work in tandem: a generator that creates new data and a discriminator that evaluates the authenticity of the generated data. This dynamic interaction pushes both networks to improve continuously. GANs are used for creating realistic images, videos, and even music. They have revolutionized creative industries by enabling the generation of high-quality, original content. These are just a few examples of the diverse world of neural networks. Each type is tailored to excel in specific tasks, showcasing the versatility of neural network technology. Each type has its strengths and weaknesses, making them suitable for specific applications in various fields. Understanding these differences is key to leveraging the full potential of neural networks in solving real-world problems. Section 6. Neural networks in action. Real-world applications. Neural networks have permeated our lives in countless ways. They power the facial recognition systems on our smartphones, the personalized recommendations we see on streaming services, and the virtual assistants that respond to our voice commands. Google Translate utilizes neural networks to provide accurate and natural-sounding translations between languages. Self-driving cars rely on neural networks to perceive their surroundings, make decisions, and navigate roads safely. In healthcare, neural networks are assisting doctors in diagnosing diseases like cancer earlier and with greater accuracy. They are also being used to develop personalized treatment plans based on a patient's genetic makeup and medical history. These are just a glimpse into the transformative impact of neural networks. As these technologies continue to evolve, we can expect even more innovative applications that will shape our future.